So in the embryology, we'll begin with the general embryology first. And before we get started, I mean, I'm sure that you all have something in common, that embryology is something which we haven't read very well in first year. We are kind of scared of embryology, and it was not covered in a sequential way or something like that. And our focus was more on systemic anatomy rather than embryology part. But not only for the PGME exam, but to build the concept for not only anatomy, but for other subjects as well, the embryology plays a vital role. So guys, we will take care of the general embryo part first. And if you have a good concept in general embryology, I can assure you right now that you will find that systemic embryology is wonderful. I mean, you'll just love it. So let's begin with the general embryo. Let us understand about the gametogenesis. Then we will talk about the first week, second week, third week of embryogenesis. We will talk about the formation of craniocaudal and lateral folds of the embryo, the different type of cavities which are formed. Because the problem is, when we read systemic embryology, even let's say if you read the cardiovascular system by yourself, now still those basic questions will hound you, like the questions like that, where the yolk sac is coming from, what is extraembryonic mesoderm, what is somatoploric, what is splachnoploric, what is primitive streak. So all these questions need to be answered, and that will be answered in the general embryo part. So let's have a detailed discussion in the general, and eventually we'll move on to the systemic as well. And embryology is a part in which you'll find certain, there are a lot of controversial questions also, in which you'll find that different guidebooks have given different answer, different authors have quoted different answers. We got to use the most standard text which is available, and I would recommend you that I would go with majority of the things which are written in Langman and the Larson's embryology. So starting our discussion in the embryology with one of the controversy only, and that is about primordial germ cells. Now, where the primordial germ cells or primitive sex cells are derived from? And guys, the answer is actually epiblast. Epiblast is nothing, it is just another name for the primitive ectoderm. Primitive ectoderm, and you have to call it primitive ectoderm because it is not the definitive ectoderm. It is primitive ectoderm, which is also called as epiblast. And this epiblast, in the second week of embryogenesis, it will give rise to the primordial germ cells. It will give rise to the primordial germ cells. Now, let's call these primordial germ cells PGCs from now. I'll be calling them PGCs, primordial germ cells. But the thing is, see, this is just second week only. Even if the primordial germ cells are derived from the epiblast, well, they cannot go directly to the genital ridge. There is no genital ridge in second week. Genital ridge is something which will give rise to the gonads, to the testis and ovary. But those future testis and ovary will develop from the intermediate mesoderm. And imagine we do not have mesoderm before third week. And we are talking about second week right now. So these primordial germ cells are derived from the epiblast. That is correct. But then these primordial germ cells will migrate to the wall of yolk sac. They will migrate to the wall of the yolk sac. I'll make you understand how exactly they reach the wall of yolk sac. So they migrate to the wall of the yolk sac. And once these primordial germ cells are present in the wall of yolk sac, and in the fifth week, by the time of fifth week, we have all these gonadal ridge and everything. So in the fifth week, these primordial germ cells, I can say, they again migrate. They again migrate to what? Now they migrate to what? Genital ridge or gonadal ridge. You can call it genital ridge or gonadal ridge. Genital ridge is something which will give rise to the testis or ovary, which eventually we will discuss. So please understand the question, guys. If the question says that primordial germ cells are migrating into the into the testis or ovary or genital ridge, where they're coming from, then you can say they're coming from the wall of yolk sac. But they're not derived from the wall of yolk sac. When the question says primordial germ cells are derived from where, then your definite best answer is what? Epiblast. It's the epiblast or primitive ectoderm, and please make sure it's primitive ectoderm, not ectoderm, primitive ectoderm, which will give rise to the primordial germ cells. In fact, this small flowchart will take almost the entire embryology discussion to understand it well, because there are so many things that probably we don't know about right now, like what is wall of yolk sac, what is genital ridge, how the primordial germ cells come to the epiblast, what exactly is epiblast. So all these questions are still, they are needed to be answered. But as I said, we have to start from somewhere, so I'm just started with this. So guys, let's start with these primordial germ cells only. Now the primordial germ cells, we said, which are derived from the epiblast, where the epiblast will come from, we'll discuss. Now these primordial germ cells, they will give rise to the gametogonium. They will give rise to gametogonium, and we know the gametogonium, when we are saying gametogonium, it's spermatogonium or oogonium. They are giving rise to spermatogonium or oogonium. So let's take them one by one and talk about the process of spermatogenesis and the oogenesis. So I'm going to start with the spermatogonium first, and let us talk about the process of spermatogenesis. There are a lot of questions asked from these gametogenesis part as well. So you will see what kind of questions to be seen there. So I'm starting our discussion with the spermatogenesis. Spermatogenesis. So as we said, from the primordial germ cells, let's say we have these spermatogonium. Now guys, these spermatogonium will undergo repeated mitotic divisions. They will undergo repeated mitotic division, and when I say repeated mitotic division, I'm talking about almost 5 to 7 cycles of mitotic division. Imagine the spermatogonium is undergoing 5 to 7 cycles of mitotic divisions first, and then it will give rise to this primary spermatocyte. This diploid primary spermatocyte is a resultant of the repeated mitotic division taking place in the spermatogonium. Primary spermatocyte, it will undergo the process of meiosis, or you can say meiosis 1. And as we all know that meiosis 1 is a reductional division, the chromosome number will be reduced to half. So we'll have secondary spermatocyte. There is a formation of these haploid secondary spermatocyte, right? That's a result of the meiosis 1. And imagine even they ask this question from here, that what is the stage for the independent assortment of maternal and the paternal chromosome? Well, maternal paternal chromosome will independently assort when the X and Y are separated. So please note that from the primary to secondary spermatocyte, or you can say meiosis 1, this is the stage for independent. This is the stage for the independent assortment of maternal and paternal chromosome. That's a direct question asked in the exam. The stage for the independent assortment of maternal and paternal chromosome, that is primary to secondary spermatocyte, or you can say meiosis 1. Now this secondary spermatocyte will undergo the process of meiosis 2, right? This will undergo the process of meiosis 2. And as we all know that meiosis 2 is an equational division. It's just like mitosis. So the resultant of this meiosis 2, there is a formation of the spermatids. These haploid spermatids, I mean these circular cells, the spermatids are formed. Well, spermatids. And these spermatids will get converted into the typical spermatozoa. They'll get converted into the typical spermatozoa. Let's say this is a typical spermatozoa here. And that process of transformation of spermatid into the spermatozoa, that is called as what? That is spermiogenesis. This is called as spermiogenesis. The process by which all these the translocation of all these organelles, the mitochondria will be arranged on the side in the line, in the neck piece. The axial filament will form the tail, acrosomal cap is formed, the nucleus will go into the head part. So all that transformation of the circular cell into the typical spermatozoa, that process is referred as spermiogenesis. But even when the spermatozoa is formed, I mean, this is still not the end of it. I mean, it's not the final stage of maturation here. So if I just may pause my flowchart here for 1 second. Now guys, what is the site where the spermatogenesis is taking place? Now we know spermatogenesis, it takes place in the seminiferous tubule. It takes place in the seminiferous tubule. Let's say this is one section of the seminiferous tubule you're looking at. And in the seminiferous tubule, we all know that we have these supporting cells which are called as the Sertoli cells. Let's say these are the supporting cells which are called as the Sertoli cells. Well, we say Sertoli cells are cuboidal cells. Well, they have these appendages on the side though. So let's presume these are the supporting cells in the seminiferous tubule, that is Sertoli cells. And these Sertoli cells, these appendages of Sertoli cells, they are connected to each other by the junctional complex, and the tight junction that you see which is present between the Sertoli cell, this tight junction between the Sertoli cell is actually the blood-testis barrier. It's the blood-testis barrier, which is a kind of misnomer here, because when we said blood-brain barrier, when we're talking about the neuronat guys, we said blood-brain barrier. Blood-brain barrier main component was the tight junction between capillary endothelium. Here the tight junction is between the Sertoli cells. Blood vessels are not participating here, but we still call it what? Blood-testis barrier. It is the Sertoli barrier, which is also called as a blood-testis barrier. It's a Sertoli barrier. And the thing to note here is, look at this, if I just enlarge it for 1 second. Now, because of these appendages of Sertoli cell, the entire lumen of the seminiferous tubule is now divided. We have some basal compartments where you will see all those primitive stages like spermatogonium. Then they will convert into the spermatocyte. You may see spermatocyte, primary spermatocyte here. Let's say secondary spermatocyte. Then we have the spermatids. And even when the spermatozoa is formed, I mean, these tight junctions will keep on breaking and reforming. And the spermatozoa, when it is formed, all these stages can be seen in the different compartments. They will keep shifting above. They'll keep shifting toward the lumen. And as I said, even when the spermatozoa is formed, you will see those spermatozoa are adherent to these Sertoli cells. They're not free, they're adherent to the Sertoli cells. And these spermatozoa, they are released in the lumen of the seminiferous tubule. This process of releasing of the spermatozoa in the lumen of seminiferous tubule is called as spermiation. That is the next thing I want to write here. Spermiation. That is spermiation. So what is spermiation? Spermiation is when the spermatozoa are released, they're released in the lumen of seminiferous tubule. Till now they were present in between the Sertoli cells appendages. Now they are free in the lumen of seminiferous tubule, right? That process is called as spermiation. So we saw that we had this process of spermatogenesis, then we had this spermiogenesis, and now we saw that as a spermiation. And still this is not the end of it. The spermatozoa, when they are transferred to the epididymis, let's say this is epididymis here. So guys, epididymis has answer to many questions here, because epididymis is the site for the storage. Number one, it is a site for the storage of the sperm. Epididymis is the site for the maturation, not the final stage of maturation, but yes, maturation takes place in the epididymis. And number three, motility. Motility of the sperm, which actually is a part of maturation only, is also gained in the epididymis. So several questions are answered here, that epididymis, the site for what? Storage, maturation and motility. And again say maturation, but not the final stage of maturation. The final stage of maturation, which is nothing but the conditioning of the sperm, is called as a capacitation. That is the capacitation capacitation, as I said, it is nothing but the final stage of maturation. Capacitation is the final stage of maturation. The question is, where does the capacitation takes place? Well, first of all, capacitation is a gradual process. It starts in the cervix itself. It starts in the cervix, it continues into the uterus and fallopian tube, but the major chunk of a capacitation takes place where? In the fallopian tube, and that too in the isthmus of the fallopian tube. Not the ampulla. Ampulla is for fertilization. In the isthmus of the fallopian tube. So if this question is asked on the capacitation site for the capacitation, your best answer would be here, the isthmus of the fallopian tube. The final stage of the maturation is called as capacitation, and that takes place where? In the isthmus of the fallopian tube. So what overall we can extract from what we discussed in the spermatogenesis, that first of all, the site for the spermatogenesis, it is what? It is seminiferous tubule, number one. Number two, time taken. Time taken for the process of spermatogenesis is actually 72 to 74 days. Not hour, guys, that is days. 72 to 74 days. 74 is your best answer if you have to choose one. 72 to 74 days. And there's one more question here, that one spermatogonium will give rise to how many spermatids or spermatozoa? And I want you to be, guys, to be careful about this question, because it says one spermatogonium, not one primary spermatocyte. If it was one primary spermatocyte, the answer is quite obvious, 4 only. Then one primary spermatocyte will give rise to 4 spermatid or spermatozoa. But the question is about spermatogonium. If you just go back and look at the cycle, we said the spermatogonium will undergo 5 to 7 cycles of mitotic division, and then this spermatogenesis will begin. So therefore, the answer is definitely not 4. The answer is 64 to 512. Spermatozoa, and if you have to choose one, I'll go with 64. There is a 5 cycles of division have taken place, and 64 could be the best answer if you have to choose between 54 and 512. Otherwise, both are correct, because 5 cycles of division can take place before it goes into spermatogenesis, or even 7 can take place. But the more accepted answer is 64. 64 is a better answer. So this is about the process of spermatogenesis, and some direct questions which can be asked from it. So moving on, now let's talk about the second process, that is the process of the oogenesis. And you can definitely expect more questions from the oogenesis. Well, simply for the fact that oogenesis is a process which begins before birth. Well, it's quite obvious, spermatogenesis is all after birth only. It is after the puberty. But oogenesis is a process which starts before birth itself, and then it is arrested for a very, very long time, and again it restarts after the puberty. So again, in case of oogenesis, the oogonium will give rise to the primary oocyte. The oogonium will give rise to the primary oocyte. The same mitotic division, they will give rise to the primary oocyte, which are diploid. And then this primary oocyte will undergo the process of meiosis 1. Just like in spermatogenesis, it will also go under the process of meiosis 1. But guys, here's the deal. We said that oogenesis, it starts before birth. So whatever we're talking about right now, this is all happening before birth. This is all happening before birth only. So what you see, this primary oocyte, which is undergoing meiosis 1, it is not completing meiosis 1. It is going to get arrested. It is going to get arrested in prophase 1. Or you can say prophase of meiosis 1. So it is arrested in the prophase 1. So this meiosis 1 is not complete. The primary oocyte is now arrested in the prophase 1. To be more precise, in which substage of the prophase 1? That is a diplotein of the prophase 1. Prophase 1, in the diplotein of the prophase 1, it is arrested. That means at the time of the birth, the female gamete, that is, it is primary oocyte only, and that is arrested in the stage of the prophase 1 only, right? So that's what we said, that during childhood, ovaries are inactive. During childhood, ovaries are inactive, so obviously no change there. So this stays like this till the puberty. But once the puberty is attained, guys, this LH surge with every cycle, LH surge, which is approximately 36 hours prior to ovulation. LH surge, which is 36 hours prior to ovulation. Approximately 36 hours, 24 to 48, approximately 36 hours prior to ovulation. And because of this LH surge, the meiosis 1 now completes. The meiosis 1 completes. Imagine the meiosis 1 which was arrested in prophase 1, that meiosis 1 is now completed. It completes. And once the meiosis 1 completes, this will give rise to the secondary oocyte, which is haploid, along with the first polar body, or called as polocyte. Along with the first polar body, or the polocyte. Well, we know polar bodies having the same number of chromosome, but the minimal cytoplasm. So basically, polar body is to get rid of extra number of chromosome. So the main thing here is the secondary oocyte, which is having the maximum cytoplasm inside and almost nothing with the polar body. And this secondary oocyte, this also undergoes the process of meiosis 2. And once again, we know meiosis 2 is just like mitosis. But will this meiosis 2 complete? Again, the answer is no. Primary oocyte was arrested in what? Meiosis 1, in diplotin of meiosis 1. Secondary oocyte is, which is starting the meiosis 2, we have the meiosis 2 beginning in it, but that is again arrested. This is arrested in the metaphase 2, or you can say metaphase of meiosis 2, same thing. It is arrested in the metaphase 2, that also is a question. And this metaphase 2, or this meiosis 2 I should say now, this meiosis 2 completes. This meiosis 2 completes only if fertilization takes place. Only if fertilization takes place, that is the way the meiosis 2 will complete, otherwise it won't. So this is about the process of the spermatogenesis and the process of the oogenesis. As I said, the chances of the questions on the oogenesis are more because the entire process of oogenesis was arrested twice. Primary oocyte was arrested in the prophase 1, and secondary is arrested in the metaphase 2. So knowing this, the spermatogenesis and oogenesis, and we said the meiosis 2 completes only if the fertilization takes place. So the next thing that we'll talk about is the fertilization and the implantation itself. So we'll talk in the embryo according to weeks. We'll talk about the first week of embryogenesis, which is all about the fertilization and implantation. Then the second week, which is about the bilaminar germ disc. Then the third week, which is about the gastrulation. So that's how we're going to discuss the general embryology part here.